To talk about heat in sedimentary basins. We are rather beginners in foreland basins, but we did a lot of work in other basins. So what I will tell you mostly is what is controlling heat in basins per se, and I will come to one foreland basin in the end. And of course what I'm showing is not only work that I did alone, but a whole bunch of people have participated in producing these results. Some of them have already left the group, so you will see a number of names appearing on publication references. So why would we be interested in heat in basins? Of course, heat is controlling a lot of processes that are related to georesources on the one hand, be it petroleum, coal, or mineral resources, as we are looking at partly in strategy. Geothermal energy, we want to store things in sedimentary basins, and we always want to know how hot it is at what depth, and if we are really good, we want even to know how hot it becomes at which time of the basin evolution. So the hypothesis is that different basins have different fingerprints, thermal fingerprints, sort of geophysical fingerprints that result in thermal fingerprints. You have probably heard about the Wilson cycle before, where you start with an intracontinental rift, you break the continent to create an ocean with a passive margin on either side, you may close the ocean again and get a subduction system with foreland basins on either side, but you also may have basins that are related to strike-slip structures or to transform faults, such as the Dead Sea fault, for example, or the San Andreas. What we want to know is how much material is deposited when in such basins, which temperature and pressure conditions are prevailing during that evolution, and then we can ask which georesources can we look for, and can we use the subsurface, and what consequences would this utilization have. For all this we need to know temperature, heat. So what we are doing is that we try first to describe the present day physical setting of different basins in different plate tectonic environments, and we do this by integrating a lot of observations. So we capture snapshots of these systems that are maybe in a different evolutionary stage of a different type, and by comparing these we can learn something about the processes. And we do this in terms of simulations. So this is a basin modeling section here, as you probably have realized, and we try to calculate the coupled transport of heat and fluid, increasingly mechanics, and also consider some discontinuities such as faults. Of course, we also look at the history, but I'm not going to talk about that. That would be another lecture. So we go for some snapshots of the thermal structure of different basin types today. We do this comparison by using a multi-scale approach, because some of the processes controlling the distribution of heat in basins are relevant at a large scale, some only at a smaller scale. For example, if I think about conductive heat transport, it will affect the entire lithosphere, so we start with a very large model on the scale of a lithosphere. If we look at coupled transport of fluid and heat, it most probably will affect only the basin fill, but may be relevant on a basin scale, so we look at the basin scale. And then if we are interested in some local phenomena, we can go to the reservoir scale, and we bridge the scales by extracting boundary conditions resulting from the larger scale to the smaller scale. And I will try to demonstrate how we do that in this lecture today. So the fingerprints we have been looking at so far are some intracontinental systems, which is the Barents Sea and the Central European Basin System, about which I will mostly speak today. We have a number of studies on passive margins, on the Southwest African margin, on the Argentine margin, on the Norwegian margin, and then we have a system here in the Arctic Canada part that is both a foreland and a passive margin system. It was first a passive margin and then became a foreland, sort of.
Well, it had two passive margin cycles, but
it had two passive margin cycles before it became a foreland.
You can describe it as a mess.
And we are just starting to look at strike slip. There is no strike slip star, as you can see, but one of the students in the room, Ershad, will attack the North Anatolian fault next. So how do we do that? We connect all possible observations, I said, and these are field observations, information from wells that tell us about lithology, stratigraphy, measure temperatures, porosities, permeabilities, densities. We use, of course, seismic, both shallow and deep, refraction and reflection. We use potential fields, and we use increasingly seismology. Deep seismology means seismic waves that travel the entire body of the Earth and tell us something about the velocity distribution in the deeper mantle. Once we put that all together, which takes a lot of time, we will arrive with a model like that has certain units with certain properties, and we can use it to calculate its gravity response, its thermal structure, its stress field. We can start to restore it, we can start to subject it to some forces. So back to heat. Heat, of course, depends on the heat source and on the heat transport mechanism. So what type of heat sources do you know? The deep earth, some more?
Radioactive.
Radiogenic heat, exactly. So we get heat from the deep earth that in the models usually we approximate with the depth position of this isotherm, which is the 1300 degree isotherm that, according to a phase stability diagram of peridotite, is the place where peridotite starts melting. We can detect that with seismological methods as a velocity reduction in shear wave velocities and some other methods. Anyway, this difference from the surface to this isotherm determines our average thermal gradient in our system. If I have a thin lithosphere, the 1300 degrees are distributed over a much smaller distance than if I have a thick cratonic lithosphere, where this isotherm will be much deeper. Second source of heat, radiogenic heat. And of course, that portion of the lithosphere creates the most radiogenic heat, that is the richest in radiogenic elements, means the more or less silicic upper crust. Whereas the lithospheric mantle and the sediments contribute a little bit, but not that much as a granitic crust, for example. So the next point is the heat transport. I guess most of you have heard about this transport mechanism, conduction. Heat is transported through diffusion. To describe that, we need to know how conductive are our rocks. If we want to know a transient process, for example, lithospheric cooling after stretching, we also need to know the rate of change. But I will just look at steady state at the moment, and so we need to know thermal conductivities of all our units to be able to say where is the heat going efficiently and where is it stored. What other mechanisms could you imagine to transport heat? So, what is convection?
Fluid circulation.
Fluid circulation. Okay, is there another type of convection you have heard about? Where is the part on Earth where we have heat transport dominated by convection?
In the mantle.
Exactly, below the lithosphere. But we are looking for today on the lithosphere and on the basin film. And we have moving fluids in the pores. And these fluids move in response to a hydraulic gradient, for which I choose this pouring from the wine bottle as a memory help. Can you see from there? Can you see here from there?
Yes,
Okay.
In case I have to.
Okay. So the fluid will move from an area of a high gradient to an area of a low gradient. We will have recharge and discharge areas. And of course, the fluid will take along its heat or cold. So is that the process that is faster or slower than conduction? Do you have a feeling for that? What would you think? Who is for faster? Arms up. Okay. 4.5. Who is for slower? Oh, no one really advocates slower. Okay, I'm happy to see that, because of course fluid movement is a lot faster than conduction. So there is also a lot of discussion about free convection, what in contrast to the advective fluid transport means the fluid moves just in response of a density difference. Could be the fluid is hotter and therefore less dense and then rises, or it is colder and sinks. But it could also be that we have something dissolved in the fluid that increases its density. Here we need to know, in addition, compared to the advective part, not only the permeability of the rocks, but we also need to know the density. So we need some constitutive laws that describe how the density is changing with salinity or with temperature. There is a lot of debate if this happens at all, and I will try to come to some sort of conclusion what we think in this debate. And because we were also interested in which of these processes is relevant at what scale, we have started to look at them individually and have run models that stepwise have analyzed these things standalone. And I'll try to demonstrate this whole workflow now with the example of North Central Europe. So you see here a model that covers an area about from the British Isles to Poland, and it's the so-called Central European Basin System, an intracontinental basin that developed on an assemblage of Paleozoic terrains that have accreted in 2 and more orogenies. The nice thing about this area is that it has been explored for petroleum for many decades, so there is a very good database on the sedimentary field, and what you see here is just compilations of sediment thicknesses for individual areas. In parts they are really based on seismic data, 3D merges and so on, so it's really high resolution data that we have spent about 15 years to compile into one model, and several generations of PhD students have been working on that. But the nicest thing about this is that we have a lot of academic deep seismic experiments in the area. So these are all either refraction or reflection experiments that illuminate the crust and give us not only the crust mantle boundary, means the moho, but also the internal structure of the crust. And there has also been a lot of seismological observations that we were able to integrate. Meanwhile, we could do better because there is even more now than at the time when we compiled the model. But it doesn't look like the model would be completely inconsistent with the new observations. And what you see here, for example, in deep seismology along the Thor experiment is that we have a very thick lithosphere. Here we have this, what I mentioned before, 1300 degree isotherm. It's 250 plus, so they don't find a shear wave velocity reduction in their observations. Then we have a step along the Sorgenfrey-Tornquist zone by 100 kilometers. We have something what we call like a Paleozoic assembled lithosphere around 100 kilometers, and then we have a thinned lithosphere. We have a thinner lithosphere towards the south even. We took all this together and fed that in a 3D gravity modeling program and have additionally constrained the different densities that we derive from the seismic velocities from the deeper crust via 3D gravity modeling. And that's what the model looks like. Just keep in mind we are 1,700 times 1,200 or something kilometers wide. Horizontal resolution is 4 kilometers, so there are things we don't resolve with that model. But we resolve quite a lot, so we have a number of sedimentary units here, and in particular we have the Zechstein salt, which in this area here in northern Germany and the southern North Sea is quite impressive, as you will see later. We have a number of pre-Zechstein units, some metasediments, when we have a crystalline upper and a crystalline lower crust that are distinguished as 2 layers of different densities, of different velocities. And in parts, of course, if we think in densities and velocities, we can derive lithologies from that. And accordingly, we will have a more silicic composition here and a more mafic composition here. And if you think back on my heat story in the beginning, this unit will produce a lot of heat into our system. The lithospheric mantle is delimited downward by our 1300 degree isotherm, and we will look at it in more detail later. So we populate the model. We start with steady state conductive, the first heat transport mechanism I was introducing. We populate the model and assign thermal conductivities to the units. We assign radiogenic heat productions to the units. Of course, this is not one simulation, but there is a whole lot of simulations behind that result. The values are partly measured values, partly literature-derived values. But what is important to note here is that we have units that are very young, sediments that are poorly consolidated. So they have a high porosity and a very low conductivity. They are insulating. And we have units like the Zechstein salt that is very conductive, 2 to 3 times as conductive than its neighbors, or its upper and underlying layers. Of course, the crystalline crust is more conductive than the sediments, as you can imagine, because there is a more compact grid how it is organized in its minerals. And it's also producing a lot of radiogenic heat compared to the sediments or the mantle or the mafic rocks. So we can run this steady state calculation of the heat equation, prescribe 5 degrees at the surface, 1300 degrees at the lithosphere-asthenosphere boundary, and get a 3D distribution of temperatures. And these temperatures are the result of a superposed effect of many different things. And I will try to sort them out one after the other. So this is a map of the 100 degree isotherm in that model. And you can see that 100 degrees are reached in Scandinavia at a depth of almost 6 kilometers, and in the southern North Sea already at 2 kilometers almost. So if you drill a well and want to have 100 degree, which is normally the place where oil is generated or where you can start electric power production from geothermal, just as 2 possible applications, you may want to know before how deep this isotherm is located. So when we look at this pattern, we see bluish colors here in the northeast and reddish colors in the southwest, cold and warm. Why is that so? The first reason for that is our average thermal gradient. If you look at the position of the lithosphere-asthenosphere boundary, it rises from, as I said before, more than 200 kilometers beneath Precambrian Baltic Shield in the northeast to something like 90 kilometers beneath the southern North Sea. So this produces an average thermal gradient that is quite different. So part of this pattern is related to this fundamental difference. If we look closer to our isotherm map, we see that there is another cold spot here. So we have a pattern of a shorter wavelength. And why is that so? That is because this is the basin margin, and there the conductive crust reaches the surface. In the basin part, we have up to 18 kilometers of sediments of lower conductivity. There the heat cannot escape. We have a thermal blanket on the system. So at shallow depth it will be warmer than compared to the areas where the conductive crust is cropping out and the heat can just go out. So this is what we will later call, at a smaller wavelength, chimney effect. It's just like a chimney. The heat goes out via the conductive crust. And the conductive crust here is at about 0 or above 0, as the reddish colors indicate. If we look closer to the map, we see that there is another pattern of a very short wavelength, a very patchy pattern of temperature differences. And these short wavelength temperature variations are indeed caused by the Zechstein salt. So what you see in the lower part is the top relief of the Zechstein salt surface. We have gigantic salt structures below northern Germany. They are 9 kilometers high. These salt walls are up to 100 kilometers long, about 20 kilometers wide, and they are channeling the heat in the system. So these salt structures have a decisive play in the shallow temperature field in this system. They are covered by, again, low conductive sediments, which makes this very short wavelength thing, because next to the salt diapir there is something insulating, so there we will have heat storage. To illustrate this a bit more, I will show you a cross-section through one of the largest salt structure in northwestern Germany, the Glückstadtgraben. And you can see we are here, this is 10 kilometers depth. The scale, you see isotherms. The colors go from 5 to 260 degrees. The shaded things are the salt diapirs. And you can see that the conductive salt extracts the heat very efficiently. Therefore, below the salt, it will always be colder than neighboring the salt structure. If there is something insulating above the salt structure, it will be hotter above the salt, because the heat is arriving and cannot go away. If the salt is cropping out or coming close to the surface, it will be like with the basin margins. The heat just goes away and it will be colder in the salt, below the salt, and above the salt. So if you cut your section and look at the map, you will have thermal anomalies of opposing polarity depending on the depth where you cut. So what you can also do with such a model is to compute the surface heat flow, what many people use to derive ideas about what is happening in the deeper lithosphere. And you can see that the salt structures cause a very high heat flow, which is reasonable, very conductive, the heat flows efficiently. And the average is a continental 60 milliwatt per square meter value. Around the margins of the basin, we see the heat flow at the top of the crystalline crust, which has smaller values, because part of the heat that arrives at the surface is also created in the sediments. So that's why these values have to be lower. But imagine you would have only punctual heat flow measurements on these salt structure crests, not knowing that there is salt. You would interpolate a positive thermal anomaly and you would say, oh, there must be a rift below. There's a high heat flow. Careful, always, when there is salt, be careful in evaluating your heat flow data. So to get a better idea how much heat is contributed from which level in the system, we cross the heat flow contribution along this section, and we will look at it here. Here you see the geological structure. In light green is the upper crust producing heat. Dark green is the mafic lower crust producing less heat. The spikes are the salt structures, the light blue spikes, and the rest is sort of insulating sediments, and here we have the Cenozoic insulating sediments. And when you think about 60 milliwatt as an average value for intracontinental, what we would also expect in Argentina, for example, the contribution to the 60 milliwatt can be quite variable. So you have areas where a large part of it comes from the deep earth. You have areas where a large part of it comes from the crust. And you have, of course, the spikes above the salt structures. So surface heat flow alone cannot be used to evaluate the deep structure. You need additional information from some other observations. So the model has been validated with a number of temperature measurements that have been collected in many different structural levels in salt structures and next to them, and shallow and deep. And what we found was that the model reproduces to a very good degree what we observe, given the resolution and the size. But there is also a part of the values that really deviate considerably and systematically. So why could that be the case? What did we not consider, apart from resolution and accuracy of the model? What else could be contributing to these misfits? You remember what I was talking about heat transport mechanisms? Any suggestions?
Fluids.
The fluids. Here we go. So what we did next was to let water flow into that. We zoomed into a little area because these computations are a lot more demanding. We couple processes, we have a lot more equations to solve. We need to have a higher resolution, both in terms of geology as well as in terms of numerics, because we consider this additional transport mechanism, and we need additional information. So we now need permeabilities. And also we need, of course, apart from the hydraulic properties of the units, we need to set up boundary conditions. We need to say how is the water flowing in. So we did that for the area of Brandenburg, which is this small setup, and we will look at the cross-section running north-south here, just actually below our feet. Later on, this is the cross-section. You see we have also here, we have the salt structures, we have a higher resolved sedimentary succession that has one very important unit, which is the Rupelian clay. The Rupelian clay is this ochre-colored part in that section, and here is a thickness map of the Rupelian clay. This is a unit that separates hydraulically the fresh water that we use and drink and comes out of the tap from the saline deep groundwater that is heavily polluted because we have the Zechstein salt. This Rupelian aquitard has holes because there was a glaciation here, and this glaciation has carved into the sedimentary succession that was already there and carved deep rims, like you see here, these light yellowish little rims. So we have holes that allow a communication between these two groundwater stories. So how will that affect the thermal field? We start with the conductive case, the same as before. You have the salt structure, some chimney effects. Apart from that, pretty flat isotherms. And the shaded layer here is the layer where the Rupelian is, and you see this interrupted here. Now we let water flow in according to a given hydraulic gradient that in this case corresponds to topography. And you can see where you have a high hydraulic gradient, a lot of pressure, and a hole in the separating clay unit, cold water can go quite deep. And the temperature field will be severely affected, so we will get significantly different temperatures in the case of considering fluid flow or not. The difference can be illustrated here with a temperature map at 2 kilometers depth. This is the conductive model with a few little spots due to the Zechstein salt. And here we have the coupled model where in the areas where the holes in the clay layer are, we get severe cooling to a large depth. Then this system has also a few faults. So the system is delimited in the south. You have seen that in the section. There is a steep fault with an offset of 4 kilometers here. So we were looking at these faults. What if they are permeable or not? And I will just show you an example for a more permeable fault than the surrounding rocks. So but we wanted to know how important is it to consider them, how far would be the influence of such a fault. And you may have such faults, for example, also in the Andean foreland. What happens if the fault is more permeable is that the fluid all goes into the fault plane and it starts to build convective cells along the fault plane. So you can have lateral temperature differences along the fault plane that are between 20 and 60, varying between 20 and 60 degrees. And the wavelength of these cells is determined by the topography of the impermeable basement and by the hydraulic head, of course, and by the adjacent units. So if a permeable unit, a shallow permeable unit borders the fault, cold water will easily flow into the fault, more easy than a deeper unit that has less porosity and less permeability. However, to make it short, I don't go into all the details of these simulations. What we learned is that the lateral influence is relatively limited. Like 10 kilometers away from the fault, there is no more difference to be seen. But in the fault, you can have significant variation. So what we learned is conduction is the most important one, heat transport mechanism. Advection can be important on the basin scale in the sedimentary fill. Convection is very local. I forgot to say that actually. If we go to that section again, you can see we have these small convective cells in areas where there is no large difference in hydraulic head, and we have a thick permeable layer. Here we can even develop density-driven convective fluid movement, taking along also heat. But that is a very local phenomenon. And if we would be more realistic in the geology and account for interbedded clay layers, probably it wouldn't happen. So free convection, very local. We did that for a number of other basins. That was an intracontinental salt-bearing basin, what you have seen. We were looking at other intracontinental systems at margins, as I said initially. And what we found was that in each of these basins, the fingerprint is really different. And Ershad is currently comparing just simply the gradients in these different systems and tries to condense the systematics in that. So for example, rifts. How do rifts look like? Here we have an example from the Upper Rheingraben. The Upper Rheingraben is located in also Western Germany and is a very young tertiary rift structure superimposed on a Variscan grain. So these are Variscan units here of different lithologies. And if we look at the shallow thermal field of the Upper Rheingraben, here is a temperature map at 1 kilometer depth. So we did the same story with integrating data and gravity modeling and so on. I come now directly to the heat part of the thing. We see a large variation. It's two-partite with a colder northwestern part and a warmer southeastern part that is not strictly following the rift structure, actually, in 1 kilometer depth. And that is related to two factors here. One is, of course, the sediment thickness that, like in the other system, will cause thermal blanketing and will store the heat. But you can see that we have a hot anomaly also in an area where there is actually no sediments, or very little. But what we have here is a very thick apocrystalline crust that is producing a lot of heat. So the heat input into the graben is to a large degree controlled by the composition of the underlying rocks. And these underlying rocks, as I showed in the beginning, are part of different orogenic units. So in some sense, it's also a Forlan system, what you see here. It's an orogenic belt where we have the outer schists and weakly deformed units here of the Rhennoherzonian, and it's going towards the internal units here. They are more and more radiogenic. And that is expressed in the thermal field. And if we look at the temperature at 10 kilometers depth, it's evident why we have this general two-partite distribution of the large long wavelength temperature pattern. Passive margins. So the rift is broken, we have created oceans. How does a basin on a passive margin look like? And for this I will show you results from two volcanic passive margins. The Norwegian margin, a 55 million year old system, and the South Atlantic margin, a more than 130 million year old system. Looking at the crust of these two systems, we see a thin crystalline continental crust that passes into oceanic crust. Both systems are very similar in the crust. The crystalline crust is thinned. We have thick sediments, we have seaward dipping reflections, we have magmatism, we have high density, high velocity bodies. But what is completely different in these two systems is the mantle. So in the rift case, you realize there the crust was the thing that was making the difference. Here, the mantle makes the difference. when we were at the step of constraining the model, that is the gravity modeling, we realized that the oceanic mantle in the northern system has a much lower density than the continental mantle. Whereas in the old system, the mantle is boringly uniform from the ocean to the continent over the stretched margin, everywhere the same. And then we ask ourselves, why is the mantle less dense here? And of course, temperature is one possible reason for that. So we tested different models and came up with the solution that the oceanic lithosphere is still cooling in the young system because it's younger and because we have the Iceland plume sitting next to it. Whereas in the southern system, we have an equilibrated mantle with a uniformly deep LAB, and accordingly, we can expect that the temperature in the basins may look a little different. So when we look at the young system, we see that in the upper 5 kilometers, this is 5 kilometers depth temperature map, the margin is the hottest, thick sediments, thermal blanketing, heat cannot escape. So that's fine. That is consistent with everything we had before. If we go deeper, 10 kilometers, we see that the hot area moves oceanward. And in 50 kilometers depth, when we are in the mantle already, we see a temperature difference, a lateral temperature difference of 400 degrees. The mantle is really significantly hotter than beneath the ocean than beneath the continent. Looking at the older system, we see also that the margin in the upper 5 kilometers is very hot. You can ignore these two because these are other basins. I'm not going to talk about these. Just look at this small stripe here. If we go deeper, it's not getting any warmer in the ocean part, but it's getting warmer even on the margin. And if we go very deep at 50 kilometers, when we are in the mantle in both cases, the continent is the hottest part. And that is, of course, related to the influence of the radiogenic heat-producing crystalline crust that is here thickening towards the continent. And because there is no signal from the mantle, it's uniformly thick, it's not making any difference. The difference is related to the crust. Finally, foreland basins. So the only foreland basin we have been looking at so far is the Molasse Basin, which is located in north of the Alps, and we've been looking at the German Molasse Basin. This is the outlines of it. We did the same thing with data integration. I will skip these parts and make it very short. This is the geometrical distribution of the units in that foreland basin. You see the strict foreland sediments are only these two units. This is the folded molasse and this is the foreland molasse fill. We have a few pre-foreland units that have different geometries, and we have the Alps next to it. So what we were asking ourselves is, what difference does it make if I stack the crust? I doubled the amount of heat production, for example. Will that make a difference or will it not? And how would this different association of rocks in the origin affect our foreland basin? And what we have in the Alps is the so-called Tauern window, where crystalline rocks, deep crystalline rocks, are cropping out and are surrounded by deformed sedimentary units in the Alps proper. So very conductive, much less conductive. This is a cross-section. You see that the foreland sediments are really thin compared to the big amount of Alps. And we have, I will just skip this, ended up with a similar lithosphere scale model by integrating all these different informations. And here again you see this Tauern body, where crystalline crust is going throughout the entire column. And if we now run, I have to skip a few slides, just ignore them, because otherwise I don't get with the time. If we now look what the temperature result would be for such a system, in the same way as we have been looking at before, again with populating all the units with conductivity and radiogenic heat production, what we get is actually a chimney effect along this tower body. And this extraction of heat will influence the temperatures in our foreland basin. And we started the whole work because there was a thermal anomaly next to Munich where people are using geothermal energy, and it's a very prospective geothermal energy because the water is drinking water. It's 100 to 150 degrees hot and it makes no corrosion. So you drill a well, you produce electrical power and you heat the community. Very efficient. Southeast of Munich they have drilled and there was 50 degrees less than expected. Same dip of the aquifer, same depth, same cover, no one knew why. What we found with this model is that a part of this negative anomaly is actually induced by this tower body in the Alps that sort of takes out heat of the system in the right place and causes a part of the negative anomaly southeast of Munich. This is just a close-up where you can see how the isotherms will be deviated due to that higher conductivity. And this is a depth temperature map predicted by that model with a close-up here. Here is this negative anomaly that's been observed. This is the observation. However, we couldn't really fit the dimension. The location was okay, but it was clear it's still too hot. The whole thing is still too hot that we predict purely conductively. So what we did next was to let water flow in. And I will show you the results of this simulation. This is the coupled model as in the Brandenburg case. We have run a basin-wide basin fill scale model which has a different discretization and which also considers different permeabilities in the whole thing. So we put everything we knew about hydrogeology, geology into that. Permeability distribution. We took the boundary conditions from the large model that we prescribed in 7 kilometer step, and these were the results. So you can imagine in an orogen, the orogen is basically here. We have a very high topography and we have a very high hydraulic gradient. That means the cold water is pressed in with a very big vigor. So, and the foremost unit in front of the orogen is the folded molasse, which is a deformed unit, which is a bit more permeable than the molasses sediments proper. So there is fluid pathways. And what happens is that we get the cold water penetrating actually pretty deep, down to 4 or 5 kilometers, getting heated up and migrating northward, depending on the permeability distribution. So when we go back to our observation, we come pretty close to this negative anomaly southeast of Munich without further fine-tuning. That's just an intermediate step of the work to show you how the principle works. It needs calibration, of course, and it's a model. Always, a model is always a model. It's never reality. And how that works, I just wanted to show you briefly. So this is the cross-section through the folded molasse. And you can see that you have, depending on your hydraulic gradient, water movement in many different ways. And these are north-south sections that clearly illustrate that the cold water comes in the south, gets heated and rises to the discharge areas of lower hydraulic pressure, advective-driven heat transport and fluid transport, to cause these very short wavelength temperature variations. These are definitely exaggerated, but the principle holds. So if you are thinking of temperatures in foreland basins, be aware that there is this very high hydraulic gradient and the fluids that are moving in the system. And I think I will stop here and give you time for some questions. Thank you.